an X-ray? Because X-ray apply electromagnetic wave. Yeah, X-ray apply electromagnetic wave. We call it X-ray. X-ray having the wavelength in Armstrong. Yeah, 2 Armstrong, 3 Armstrong. You know, 1 nanometer is 10 Armstrong. Yeah, so please do you remember? Yeah, one nanometer is 10 Armstrong. So X-ray range will be 2 Armstrong, 3 Armstrong, for example, until 30 Armstrong. Yeah, so it's high energy. While ultrasonography, it's applied the mechanical wave, but the frequency is ultrasonic, above 220,000 hertz. Yeah, so we have infrasonic, and then audiosonic and ultrasonic. So ultrasonic, the frequency is above 20,000 hertz. But for X-ray, it has let we calculate. Yeah, what 10 Armstrong. Yeah, so if we convert it into hertz, it will become 300,000. Okay, over here okay. Wow, it's high frequency, 1 million trillion hertz. 1 million trillion hertz. 10 1 to the power of 18 hertz. Yeah, so it's high energy. Yeah, so this, okay. So and also electromagnetic energy. Yeah, so this the principle of X-ray. As we know, we apply the high voltage, yeah, of electron in the high energy, yeah, capture or vibrate to anode and scatter the X-ray. So this is the condition happen when electron, yeah, collide with the nucleus, yeah, in high speed, yeah, fast incident electron, and also electron scatter, yeah, scatter. The scatter of electron will receive energy by the nucleus, and yeah, it escape X-ray energy. Yeah, like a collision. Yeah, so it releases an energy, right? But the incident happening to electron and nucleus. Yeah, this is the way to what produce X-ray energy. Yeah, so here, yeah, generate electron, and we have it result X-ray energy. So in high energy, so this energy. Okay, but the question, sir, what is the purpose of X-ray diffractions? Yeah, the purpose of X-ray diffractions is to understand the pattern of the atom. Yeah, the pattern of electron atom in the lattice. So like us, we have a single crystal, as I shown you last week, right? So this is the pattern of the atom. So this is the function of X-ray diffractions. When the electrons scatter in a different angle, yeah, 2 theta, we call it 2 theta. So the light intensity or the intensity of the wave received by the detector, the energy was counted, and we will see its peak. Its peak will indicate a crystal lattice, crystal structures. The crystal structures could be BCC or FCC, yeah, and also here refer to bidang, yeah. What's the name? When we call it, for example, 100. In here 111, the example, and this one 112, yeah. So we will discuss it later. Okay. So this is the phenomenon happen. I will show the video after this slide, yeah. So please wait. So when there is X-ray energy, yeah, X-ray wave, yeah, and also affect to the atom, yeah, collide with the atom will scatter the energy here in a different angle. The phenomenon, we call it as diffractions. Yeah. Sorry, I need the water. What is D, sir? D is the distance between two atoms. Okay, could you listen my voice?
Yes, sir.
Yes, sir.
Okay, and then lambda. Lambda is the wave of X-ray. Yeah, wavelength of X-ray. What is sine theta? Sine theta is the angle here. The diffracted angle. This is 2 theta. Yeah. Why we make it 2 theta? Because there are a video afterward. This is the detailed explanation. Look at here. Refer to look at the wave. Yeah. This is firstly the phenomenon of interference. But when it happening into the narrower lattice, yeah, the lower narrow zone, while the angle of wave propagations scatter, yeah, so it create like a collision, but we call it scatter, yeah, so it was diffracted. By the end here, the intensity was detected, yeah, so it result the peak afterward. The relation, look at here, it's half wave, right? Half wave, yeah. And also this one refer to D. D, look at distance between two atom. Yeah. So X-ray, by the way, can be used to measure the distance between two atoms. Yeah, in the lattice. Yeah. Okay. So look at another calculation. Look at theta. Yeah. Do you remember sine? What is the meaning of sine? Adjacent. Hypotenuse, do you remember? Okay. Okay, yeah. So here phase to half lambda, yeah, over D, yeah. Okay, so I got hypotenuse. So this one lambda over 2 over D. This is refer to N, yeah, 2D. Okay, after this one and lambda over 2D. Okay. Why we need here N lambda? Because wave has the same pace. Yeah, do you remember in wave and optic? Yeah, pace. Pace can be repeated. Yeah, 1 wave, 2 wave, 3 wave, 4 wave. It will result the same intensity, right? You are confusing, but I want to engage you into a detailed investigations of modern scientists. Yes, it is a modern scientist. Yeah. So there is no another way to identify atomic properties. Although, you know, if I want to measure Mufti, yeah, Mufti Haig, I can use ruler, right? Yeah, ruler or another. But if I want to measure a distance between atom, we can only use a light, because a light wavelength approach a distance of atom. Yeah. Okay. And afterward, we identify the crystal structures. Yeah. As we know in X-ray, we orient. Okay, there are a different angle when it's scanned, and afterward create a different diffraction pattern. Yeah. So here the Bragg law. Yeah. And this is, we call it as Miller indice, yeah, or lattice parameter. Yeah, like in the room there are length and then width, and then height, right? Height, right, this. But in atom, we do not call it length, width, or height, but we call it ABC or HKL. This is H, and this is K, and this is L. Yeah. And this is also the relation between distance between atom in the lattice, okay, reflected to here HKL. Yeah, HKL or Miller. Yeah, we call it Miller index. Yeah, Miller index. Okay. Wow, it's very detailed, but afterward here, that's the outstanding investigation by a scientist. Because by this X-ray diffraction, we can analyze the material. Yeah. Nah, this one is also the equipment used for X-ray. Yeah. Braglow and afterward. Here is X-ray. In detail, I can also show a real photograph in the laboratory of X-ray. When I was studying master degree. Here, maybe I can show you the X-ray apparatus. Do you know how expensive X-ray? 4 billion rupiah from one equipment. 4 miliar ya. 3 until 4 billion rupiah. It's very expensive, right? Any question, please? Sir, what is the relation, sir? But I am a scientist for junior high school. Is it needed to learn X-ray? You know, there is no problem for you. Yeah, if you can increase your understanding on science, yeah, it will be beneficial for your life, right? Yeah. So sometimes you will need it. Now you do not aware, but finally maybe you may think that it will be useful for another purpose. Yeah, I believe a teacher having a deep understanding will show a better explanation to student. Yeah, to explain the similar phenomenon. Yeah, for example, previous IPSC student, they discuss the same phenomenon, but they not explain it very detailed because you understand the phenomena of atomic structures, so you can explain it many detail, make somebody satisfied with your explanation because you relate physics and chemistry in one discussion, right? It's only in this course, yeah, it is the real integrated science. Physics and chemistry, yeah, we discuss it. We do not differentiate whether it is physics, sir, that's not chemistry. Or here is chemistry, sir, it's not physics, but yet it is science, yeah, material science. Here, this is here, we call it as sputtering. This is the atom. When the atom bombard here, have I shown you before? I forget. Here, I put the film, yeah, here, and also this one is target, yeah, PT target, platinum target, and you know there are argon here, argon gas, yeah, argon gas, and argon gas bombard this material, and afterward this atom, yeah, spray here, and afterward our film getting PT, yeah, or platinum atom from the target. Yeah, this is the phenomenon when the atom excite from its crystal. Yeah, it's the time to break a family. For example, a mufti, yeah, has a wife, for example, Agnia, and also Arni. There are 4 options, right? That's the time for you to break down. Yeah, peer bonding to Agnia and Agnia and seeking another pair. So that's the time. Yeah. We call it the sputtering. Okay. Clear. Oh, so sorry. Okay. How to search another phenomenon? It's still annotating. Oh, we have to delete it first. Sorry. Oh, why I cannot jump to another slide? Oh, here? It's wrong. Why I cannot show another image? Sorry. I have to seek the image first, but okay lah. We just skip. So this is X-ray. Yeah. So afterward, here the analysis of X-ray. Yeah, it results a peak representing a crystal. Yeah, representing a crystal. So the way to see the atom of X-ray, we can interpret also the afterward we can analyze. It's also the example. Well, yeah. From a paper, X-ray diffractions. Any question, please? If you have questions, I can help. Here is the example of X-ray diffraction peak. Mufti, here. X-ray diffractions. X-ray diffraction pattern of titanium dioxide nanoparticle having anatized and rutile phase. Yeah. How is anatized phase? You can search on internet here. Anatized crystal. Yeah. So a specific or particular material having a different crystal structures. Okay. This is the orientation of how crystal in anatized material. Here, the arrangement of atom in the crystal. So stone having a different crystal, and we analyze it through X-ray diffractions. Okay, so here is the X-ray diffractions. How to analyze this X-ray here? See figure 2. Here this is the example of how we analyze. Depict X-ray diffraction of titanium dioxide particle having anatized and rutile peaks. Here, the graph indicate a nanoparticle result the structures of mixed anatized and rutile. Photoelectrode contain 87.8% of anatized, confirmed by diffraction peak. Here Miller index, blah 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 blah. Okay, yes, the degree and also another crystal of the material, and this is the evidence. According to the grain size calculation, we can found the size of the crystal. You know, when Dalton, cutting a device into a smaller part, it will result approaching 20 nanometer. So this is a size of the grain. Of here. Smaller crystal size of the particle will facilitate higher number of pigment attached on the film. Okay. This is the evidence. That's a crystal. This is a crystal of material. When we see it using electron microscope, look at this is a size within 500 nanometer. Yeah, when we zoom it, look at within 100,000 times magnifications. Wah, diperbesarnya sampai 100.000 kali itu. It's powder. Yeah. And we will see here the grain of atomic titanium dioxide. Look at this is. We calculate the average size of the grain will be 24.62 nanometer. Wow. Okay. So that's a film. Yeah. This is crystal analysis. Okay. Any question, please? Now we will see. We have identified crystal structures, right? And then atom, and then electronic excitations, okay, and then band gap, and then semiconductor, and then orbital, and then valence band, and then conduction band, and then what else? Hole. It is electron. We have many terms. We discuss it. Is it the first time you heard this term? Okay. So let we continue to our real activity. Yeah. So we have now these properties, yeah, of modern physics material investigation. But now, how to make it? Okay. So how to make a film? Yeah. So that in the future, maybe you will be able as material science researchers. Yeah, Mufti. If you are challenge continue not only in science education, sir, I want to go to apply physics. Wow, because I like it. Yeah, just continue it. Because now you have learned yeah, material science. Or risky, yeah, if you are challenged going to Japan studying pure science, apply physics, yeah, or apply chemistry, yeah. So we like a jumper, binding the understanding of science not just on the surface, but we study until the deep of scientific understanding. So you will feel a different thing compared to another course type. Yeah. Okay. So now we continue to our meeting we expect today here. Okay. Thin layer depositions. Yeah. According to the thin layer technology. Yeah. So by the end of the day, people are seeking of clean energy, right? Because clean energy could receive or reduce global warming. Wow. So risky studying global warming for research topic. Yeah. Wow, discussing blah, 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 blah. Yeah. But how to realize it? Yeah. So this one of the activity, a real activity can be done to see how can we create or make a solar cell device. Yeah, by thin layer depositions. Here, we will start from modern physics history. Oh yeah, I have to share with the sound. Do you need the break time for 5 minutes? If you want to break for a while, yeah, okay. Or just continue. Okay, you can go to restroom, yeah, for 5 minutes and we will come back again after 5 minutes.
All right, sir.
Okay, ready to start?
Yes, sir.
Okay, so I share with the sound. Okay.
Hi, welcome to our first official lecture video about modern physics. This time around, we will be studying the history of the development of modern physics. We can say that in a picture, the development of modern physics can be captured by the ideas contributed by these scientists. Mainly, we have Aristotle, Isaac Newton, and then Albert Einstein. The ancient Greeks held the record of a systematic effort of studying motion. Aristotle studied natural philosophy based on the assumption that every substance in the universe has a proper place, and that motion occurs because a substance tries to achieve its proper place. With this, time was given a similar absolute meaning that it is moving to achieve some end goal. For 2000 years, this Aristotelian physics was embraced. The latter part of that year, an Italian scientist in the name of Galileo Galilei established the importance of experiments, which disintegrates the concept of Aristotelian physics. It was in his famous Leaning Tower Pisa experiments that debunked the concept that heavier object moves faster than lighter object. 100 years later, Isaac Newton generalized the results of Galileo's experiments. With this, he successfully established the three laws of motion. It was in this time that the Aristotelian physics was completely abolished. Multitude of major discoveries and physical theories have been developed in the next succeeding 200 years. Most of the latter failed the sophisticated experimental tests. Newton's theories had been joined by equally impressive laws of electromagnetism and thermodynamics, made possible by James Clerk Maxwell and Sadi Carnot in the dawn of 20th century. This remarkable event made the scientific community believe that the description of the physical universe was complete. Albert Michelson even said at the end of the 19th century that the grand underlying principles have been firmly established. The future truths of physics are to be looked for in the sixth place of decimals. Such optimism turned out to be premature, as there was vexing cracks in the foundation of Newtonian physics. The two cracks were mentioned by Lord Kelvin in his famous Baltimore lecture in the 1900s. These were the blackbody radiation and the famous Michelson-Morley experiment. Now, in the blackbody radiation, the object absorbs all radiation incident upon it and re-radiates energy, which is characteristics of this radiating system, and not dependent on the type of radiation which is incident upon it. The radiated energy can be considered to be produced by resonant modes of the radiating object. The classical thermodynamics predicts that as the wavelength of this distribution decreases, the temperature increases. Unfortunately, this was not the case as observed here. The temperature drops out when the wavelength
What is the effect
decreases.
of this black body radiations? Yeah, we refer it to the sun, yeah, or the star color. Yeah, do you remember in in Earth and Space Science? Black body radiations, yeah, wind theory, yeah, and Michelson-Morley experiment. What is the purpose? to identify the chemical characteristic, organic compound. So by FTIR, have you ever heard Fourier transform infrared from Burika? FTIR is used in order to identify covalent bonding afterward. So the people, after finding this foundation of science, will find the new technology. What is the technology find after Carnot found? The people create engine. So people create engine. What the people do after Einstein find the theory of relativity? People create solar cell. Yeah, it's used nowadays. Yeah, and also it mimic the photosynthetic activity, right?
For the case of the Michelson-Morley experiment, the experiment compared the speed of light in perpendicular directions in an attempt to detect the relative motion of matter through the stationary luminiferous ether, and the result was negative. That means there was no significant difference between the speed of light in the direction of movement through the presumed ether and the speed at the right angles. The development of the theories of quantum mechanics and general relativity dispelled the cracks of Newtonian physics and give answers to various puzzling phenomena. The application of these theories to microscopic systems such as atoms, molecules, fundamental particles, and to macroscopic systems of solids, liquids, gases, and plasmas has given a deep understanding of the intricate workings of nature and has revolutionized our way of life. That's where modern physics born. Thank you for listening, and I hope to see you soon in our next video, which will talk about
Okay, so thank you very much for the explanation. We will go to another slide. Now here, photoelectric effect to solar cell. Yeah, this is the first foundation of modern physics, and people nowadays use it for many purposes. Not only for solar cell, but now people found computer, right? People found Android phone. It apply modern physics concept, yeah, inside.
We're in the demo lab with Lonnie, where he set up a photoelectric effect experiment. He has white light impingent on a metal, and the energy of the photoelectrons emitted are shown on the meter at right. If he puts a red filter in the path, now only red photons can strike the metal, and you can see they do not have sufficient energy to eject photoelectrons. If we go to higher energy photons, say go to yellow light, that's shorter wavelength and higher energy photons, they may be able to eject photoelectrons. And indeed, photoelectrons are emitted, but with a relatively small energy. If we go to higher still photon energy, green wavelengths, that's shorter wavelength still, higher photon energies, we can see photoelectrons emitted at a higher energy. Now we can still go to higher energy photons. Blue photons, photons in the blue region, are the highest energy visible photons, and Lonnie has a blue filter that will pass only blue photons. Putting the blue filter in the path shows photoelectrons emitted at the highest energy. So here's an example of the photoelectric effect. Thanks, Lonnie, for that great
what can you
demonstration.
conclude from the observations?
May I, sir?
Mufti? Oh, Kediki, please.
The smaller the color wavelength is going to be higher energy level, and the higher energy level is going to be having the higher photon energy. So for the example, the higher wavelengths, the red filtering is going to be having a low energy because it has a high wavelength and low energy level, while the blue one having a small wavelength but have a high energy level. Is that it, sir?
Yeah, that's correct. So afterward, it can excite electron into greater energy level, right? Okay. Next here. But now how to realize thin film technology in the solar cell?
The scope of the lab is really to think again how light interact with solids and how we can convert solar energies into electricity, or how we can store solar energies into chemical bonds. So it's really how you can collect effectively solar photons using thin film materials with specific optical and electrical properties, and how these photons can be effectively converted into electrical charges. Thin film technologies are really ways to deposit an alloy with specific elements onto a substrate, and the main way to create these thin films is really with vacuum chambers, again, where you have the physical piece of metal. Either you can evaporate that metal, or you can bombard this metal with ions to create a vapor of a specific element. And again, this plume is going to just travel into the vacuum chamber and eventually condense onto the substrate to form your thin film. In terms of efficiency, I would say thin films and standard crystalline silicon are pretty much at the same level, at about 23 to 25% solar to electricity conversion. The reasoning behind using thin films is really to try to reduce either the weight or the cost. And the cost to create these solar panels would be greatly reduced if you use cheap synthesis processes as opposed to vacuum-based technologies. What we try to do in my lab is to replace these very costly and labor-intensive techniques with cheaper methods using molecular inks that contains already all the chemical elements. We can formulate and create this ink directly in the glove box, and we can essentially print or spray these inks onto a substrate. We don't need a vacuum chamber for this. We don't need high power. We don't need vacuum pumps. This type of approach allows us to study new materials that simply cannot be deposited with vacuum techniques, either because they are not compatible in a vacuum chamber, or they just require very high temperature to be evaporated. When you report efficiencies in the PV world, on the solar world, you have to do that under very specific illumination conditions. And so instead of being outside and waiting for the sun and the weather to cooperate, we actually have an artificial sunlight in the lab.
We have this equipment in our lab.
All our tests in the lab, comfortably sitting behind the computer.
We have this
with the
equipment
AC
in our
running.
lab.
We work with Stanford University, the University of Nevada, NREL, as well as Lawrence Livermore National Laboratory. So it's really through the collaboration that we actually flourish and expand our research really here in Hawaii. I should say that the work that we do in the lab is not necessarily out for commercialization yet. Still looking at technologies that could be applied maybe 10, 15 years from now. And I think as far as HNI is concerned and the collaboration that we have, it's extremely important to look at the technologies that are today and see how these technologies can be integrated in the grid. And overall, could we even add more of these PV modules onto the grid with the help of storage as batteries or through the integration of fuel cell and hydrogen technology.
Are you interested? Do you want really to apply it in the real lab? So let's see here. That's the simple thing, Rizky. As we know, LED composed of semiconductor, right? So the people here, he made solar cell from LED, real LED. So it's creative.
LED, which stands for light emitting diode. When we apply a power supply into LED, then it lights up. Everyone knows that. But there is something that we don't know, which is if I remove the source and expose the LED directly into sun, then photon hits the PN junction of LED and generates electron hole pair, and the LED produces electricity. So if I expose thousands of LEDs into sun, does it really charge my smartphone? LED comes in various sizes, also in various colors. So it is quite challenging to choose the right LED for this purpose. So I have collected several LEDs and started testing it under the sun. But as the light intensity continuously changes due to the cloud, so I was getting inconsistent results. That is why I have used a 135 watt constant light source, using which I am getting similar results like outdoor. So I tested those LEDs one by one and made two bar graphs, one for generated voltage and another one for generated current. I am quite surprised to see the result. I thought the transparent white LED will produce more energy, but surprisingly it produces the least amount of energy, whereas this yellow one gives the maximum output. So I bought 3000 yellow LED to make the solar panel. One yellow LED generates around 1.6 volt. So my plan is to...
we will prove this is evident in lab, yeah. I know here because I want to prove it directly in our lab, yeah. I have the equipment and we will see the efficiency of LED solar cell. It's unique.
To connect 3 LEDs in series to get around 5 volt and connect the rest of the LEDs in parallel to increase the current. I first thought of making it using Vero board, but connecting thousands of LEDs in series and parallel is a very tedious process. Then my friend PCBWay told me that they will be more than happy to sponsor this project. So I quickly made a circuit and ordered it into their website. If you don't know anything about PCBWay, PCBWay is one of the most popular PCB manufacturer out there. Besides manufacturing high quality PCBs, they also provide professional assembly services. If you need any PCB for your project, feel free to try out those services. After getting the PCB, I immediately started soldering.
Parah.
Finally completed. That took me roughly 3 days to solder. Now let's connect them and check if everything is fine or not. Okay, now moment of truth. We are getting around 5 volt. So far so good. And short circuit current is around 86 milliamp, which is not that much great, but I can store the energy into the battery and use that later to power a light or a low powered fan. Even I can charge my smartphone up to few percentages. So is it really a good idea to build one?
You can realize it. It's a creativity, right? Why not you want to try it to prove the evidence directly? Okay. So, but now we continue our content today. Yeah, this is about how to create the thin film. Also, this is the term we have to know. 1 atmosphere is 760 torr. Yeah, or here Pascal. Yeah, 1.013 times 10 to the power of 5 Pascal. Yeah, 1 bar equal to 750 torr and so on. Yeah, so let's see here. And this is what we want to describe. Yeah, introduction of thin film depositions. As we know, when we deposit a film, maybe we have to consider stoichiometry of the material, what is stoichiometry, Agnia? In the chemical reactions, what is the meaning of stoichiometry?
The meaning itself, I forget.
Oh, for example, here, salt. What is stoichiometry of salt? Here, is it the stoichiometry? Sodium chloride, right? Yeah, if it's non-stoichiometric, it will be sodium 1.5, chloride 0.5. It's non-stoichiometry. Another example, what else? Please send me one example. Here, zinc oxide. This is stoichiometry of zinc oxide. For non-stoichiometry, zinc oxide could get here 0.8, 1.2. Stoichiometry. The atomic is not exact. Have you ever seen? No. I believe Burika or Bu Eli will not tell me this non-stoichiometry of chemical compound. Yeah. Epitaxy. Yeah. What is epitaxy? Do you know bata? Bata apa bata? Tukang bata nih. Building block. And afterward they create here uniformly. Yeah. And then here the growth of atom. Yeah. Vertically we call it epitaxy. Yeah, epitaxy. Morphology is the same. Yeah. I believe when I am seeing Agnia, your face is different from Dea, yeah. It's only Agnia. It's very special. Yeah. It's only when I consider your face, we will recognize you as Agnia. Yeah. So that's Allah give us a specific characteristic of our face, right? So this one is morphology. Thickness. Yeah, thickness, ketebalan. Yeah. And also another thing of manipulation of properties. Could you remember the previous thing? Doping, right? We manipulate. Or catalyze in chemistry. Do you remember? Catalyze, yeah, to reduce what? Action energy, yeah. Reactivation energy, yeah. Remember? Catalyze. What else? Yeah, so yeah, just continue. Okay. Atomic layer by layer, yeah. Like I give you an example how to grow an atom in the layer. Yeah. Here, if we have an atom above the glass, so the glass here we call it as substrate. Substrate. So substrate is like soil, is ground, and layer by layer like your house. You want to build a house above the ground. So the ground itself we call it as substrate. Yeah. Well, here we call it as atom. Yeah, the source of the atom we call it as precursor. Precursor. Precursor is the material used for chemical synthesis. Yeah, for atomic deposition. Yeah. Okay. This is the phenomena of diffraction in detail. Yeah, previously I give you in the slide, right? But now you can watch the evidence of diffraction by viewing this video.
In a single crystal X-ray diffraction experiment, a crystal is placed in the center of the instrument. The crystal is constantly rotated in a beam of X-rays, and a two-dimensional detector records the signals from the sample. From the position and the intensity of these signals, the three-dimensional structure of the sample can be unambiguously determined. Many minerals such as diamond and salt, organic molecules such as sugar, and drugs such as salicylic acid appear as small crystals. In these crystals, atoms, ions, or molecules are arranged in a highly ordered structure, forming a crystal lattice that extends in all three dimensions. This crystal lattice acts as a diffraction grating for X-rays. It is at this scale that the story of single crystal X-ray diffraction begins. X-rays are high-energy light with a repeating period called a wavelength, or lambda. Since the wavelength of X-ray light is similar to the distance between atoms in a crystal, X-ray diffraction can be used to determine the distance between atoms in the crystal. To understand X-ray diffraction, we first have to look into wave properties, called interference. Very similar to throwing two rocks into the water, the circular ripples that result from the two stones seem to pass through one another as they propagate out from where the stones entered. This is known as interference. If the waves are in alignment, the signal is amplified. This is called constructive interference. If the waves are out of alignment, the signal is destroyed. This is called destructive interference. When an X-ray encounters an atom, its energy is absorbed by the atom's electrons. Electrons occupy special energy states around an atom. Since the absorbed energy is not large enough to release the electron, the energy must be re-emitted in the form of a new X-ray with the same energy as the original. This process is called elastic scattering. In a crystal, the repeating arrangement of atoms, ions, or molecules forms a lattice with well-defined repeating distances. When planes in these lattices are exposed to an X-ray beam, X-rays are scattered by this regular arrangement. Strong amplification of the emitted signal occurs at very specific angles where the scattered waves constructively interfere. This effect is called diffraction. The angle between the incident and scattered beams is called 2 theta. For constructive interference to occur, the scattered waves must be in alignment, meaning the second wave must travel a whole number of wavelengths. In this case, 1/2 of a wavelength is traveled on the incident side, and 1/2 of a wavelength is traveled on the scattered side, resulting in 1 additional wavelength. In the case of the next X-ray, 1 wavelength is traveled on both the incident and the scattered sides, resulting in 2 wavelengths. This reinforcement occurs throughout the crystal. The exact angle at which diffraction occurs can be determined from the red triangle. The angle at the top is theta, half the angle between the incident and scattered beams. The long side is the distance between the atomic planes, and the short side is 1/2 of a wavelength. The relationship between the diffraction angle and the spacing between the atoms can be determined by applying the sine function. Rearranging this equation yields an equation commonly known as Bragg's law, named after Sir William Henry and William Lawrence Bragg, the father-son team who won the Nobel Prize in 1915 for their work analyzing crystal structures with X-ray diffraction. Today, the technique of single crystal X-ray diffraction is used to determine the 3-dimensional structure from a wide variety of crystals. Single crystal X-ray diffraction helps scientists to identify the products resulting from chemical reactions and to understand the mechanisms behind these reactions. Single crystal X-ray diffraction is also applied to determine the structure of proteins, which play a key role in all organisms, including humans. For example, our ability to see light depends on a protein called rhodopsin, located in the retina of our eye. Single crystal X-ray diffraction helps to understand the mechanisms behind seeing. Similarly, the detailed knowledge of protein structures is essential to develop new, life-saving pharmaceuticals. Single crystal X-ray diffraction provides important information to finally understand the interaction of new drug candidates with the proteins in our body. As scientists push their ability to engineer materials on the atomic level, single crystal X-ray diffraction becomes an increasingly important tool in their toolbox. Advances in equipment design have made single crystal X-ray diffraction easier to use and more powerful than ever.
Wow, interesting, right? Wow. So modern physics connected to chemistry and biology. So here is integrated science course. Okay, yeah. Let's continue to another slide. So how do we interpret the position of atom in the plane? As we call it lattice. Jadi bidang kristal itu kita namakan plane, bidang. Lattice, kisi. It look like racket, racket, badminton, racket. There are intersection between line of racket, so it creates lattice, or we call it kisi. Kisi or lattice, in English, there is a pattern that we have to characterize and we have to understand. By understanding the lattice, so we can perform our active experiment to see what is the effect of what we do in the laboratory affecting to the distance of the lattice or the plane of the crystal. Yeah, and also the grain of the crystal, and also the morphology of crystal, and the epitaxy growth of the crystal. Wow, many things, yeah. So that's material science. So look, this is lattice understanding, crystallography in the reciprocal space. This is also the phenomena as we find it in the X-ray graph, Mufti. Yeah, I have shown you in the X-ray graph. Yeah, so that's only analogy. Yeah. Yeah, so this is the description of reciprocal lattice. You see, yeah. Okay, what next? We want to show you here how to manipulate the material. We have many strategy. We call it substrate influence or finite size. Yeah, the thickness of the material, or epitaxial strain, band gap. Yeah, or level splitting or artificial stacking. Yeah. Okay, here. So how to make thin film itself? How to arrange atom in the substrate? At least there are two methods. Yeah, physical method and chemical method. Yeah, to make a thin film. Yeah, thin become a solar cell. The method we call it as evaporation of physical method, sputtering, or we follow a chemical method. The term we know the device chemical vapor depositions, low pressure chemical vapor deposition, or plasma enhanced chemical vapor depositions. What make it different? Look at chemical deposition means rely on chemical reactions in high temperatures to deposit a solid film in the surface. While a physical vapor deposition, it does not include the chemical reactions during its evaporations, during its depositions. Yeah, directly deposit a source material onto given substrate. Yeah, in the same of the source. Yeah. Okay, this is the chart. Yeah, physical and chemical. This the mechanism. Yeah, look at there are mechanical vacuum, high pump, and thermal evaporations. Sputtering principle also, it bombards an atom. Okay, so as consequence, it will result a film afterward. Yeah, as I show you in the image here. Here, sputtering phenomenon. We directly conduct it in the laboratory. This is in Japan. There is also in ITB also, but in UP it is not available. Here, can you see? This is the phenomena of sputtering during depositing a film. So I put the film, this one. Firstly, here into vacuum. Yeah. After vacuum, insert argon gas. Yeah, argon gas. And afterward, we put also before that here, substrate over there. Substrate. And also this is target. Target we use as platinum. This made of platinum. And also here, connected into potential difference. You know how large potential difference? 100,000 volt. Wah, sudah. Yeah, so it's very dangerous. So in a high voltage, so it's bombard this one, and also the atom, yeah, excite also from that surface, and here precipitate into the substrate, and afterwards substrate will become a film. Yeah, that's the way of how to make solar cell thin film depositions. Physically, yeah, physically, not chemically, physically. Yeah, sorry, why I stopped the share screen. Okay. Oh yeah, is there a result of thin film made of this material? Here, can I share? Oh, it's lagging. Is any question, please? So maybe we can discuss it more.
Sir, I wanna ask question.
Yeah, okay. Okay.
About the use of solar cell in daily life. So as we know that before, the solar cell itself is something that we call it bahasa mahal in Indonesia. So how about the effectivity of the solar cell in use in home? And then I read some sources that the solar cell, the residue or the limbah of solar cell itself is not in bahasa we call it is not terurai in long period. So is it okay? And then how do we find the solution of that problem, sir? Because I wonder that a lot of people that now currently use the solar cell, but the limbah itself is not terurai in a long period, and then I think the effectiveness is not good because the price itself is not cheap at all, gitu, sir.
Yeah. So depend on here. Depend on the perspective. Yeah, that's why we need the research, Mufti. First, how to find out the material which is environmentally friendly. So we do the practical work in the laboratory, Mufti. Yeah, to seek another metal which is environmentally friendly. Yeah, which material is it toxic? Silicon, is it toxic or not? No, silicon is not toxic. But to make it toxic is cadmium or telluride. Telluride or cadmium, is it toxic? And also here, what else? Antimony or gallium, is it rare, scarce material? So we do the activity in the laboratory using copper. Copper is environmentally friendly and easy to reprocess the unused material. Yeah, so we do titanium dioxide. You know what is the purpose of titanium dioxide? To make Agnia more beautiful. Yeah, because titanium dioxide could whitening your skin, protect your skin from sun energy. Yeah, and also what else? The material, is it environmentally friendly? Zinc. Okay. What else? Tin. Yeah. So we are seeking the material and then understand the electrical properties of semiconductor when it mix it into semiconductor. For example, copper is conductor, yeah, Mufti ya. Zinc is conductor and tin is conductor. But when copper, tin, and zinc, we mix it together and bind with the sulfur, it will be semiconductor. So because of the arrangement of the atom in the crystal, the arrangement of atom in the crystal will create it as semiconductor. Yeah. So how effective? You may think that if you buy solar cell, you have to pay it within 5 year, yeah. So you need to pay the electricity cost for 5 years, but 15 year you get the electricity free. Yeah. Are you interested to choose solar panel? You have only to buy electricity within 5 years. Yeah. Just for one time. But afterward, within 20 years, you will get free electricity. Yeah. Which one? Is it cheaper, the conventional electricity or solar cell?
But I don't know here because sometimes it need the maintenance itself. So
Maintaining of the solar cell is very easy because solar cell, to maintain solar cell is just clean it from the dust. It's very cheap and no need to real detail maintaining. It's only you need sapu and clean it, so solar cell will work it effectively again. So very easy to clean solar cell, Mufti. And also after 20 years, I feel like if you have a car or motorcycle, will you use it for 20 years? I don't think that you will use the same car for 20 years, right? Or your motorcycle or within 20 years. And have you ever think what will happen on your bike after 20 years? You will give it extras toward your tires. Which one is harder? Okay. Throwing a trash of motorbike or solar cell. So depend on our perspective. And also another purpose of solar cell, I believe that solar cell having free carbon dioxide, yeah, emission to the environment, and also make our clean energy. Yeah, people in the rich country such as Europe or America, yeah, or also China or Japan, they respect to environmental friendly pollutions, yeah. So how to reduce the pollution to conquer global warming effect. So if you want to be participated in green energy researcher, just welcome into solar energy researcher, Mufti. So will be a solution of the world problem. Wah, itulah ceritanya tuh kayak apa? Apa tuh namanya itu bla bla bla-nya itu kayak gitulah ya. Okay. Look at when we make it as a thin film or arrange the atom uniformly. Look at it's very beautiful. Look at test the atom, we form it uniformly within 2 micrometer. Yeah, it's beautiful in my side. Here is the example of solar cell we make. This one, look at here, solar cell. Yeah, flexible as well.
Screen is not shared.
Ya Allah, I'm sorry. Here, solar cell. Yeah, and this one of the atom I show you. Here, look at a good atomic arrangement. Wah, itu kayak apa ya? Jaring-jaring. It is an atom. What next? Here. This is also as you see from the video previously, but this a real activity we have do in the lab. Wow. And also this is the condition of laboratory in some university. I feel that it's not TD and not neat. Look at, wow. Wow. It's too far away from IPSC lab. IPSC lab is very clean. Which one is better, Mufti? This lab or IPSC lab? That's my questions. Yang mana Mufti yang bagus? Sorry.
Banyak alat-alatnya.
Look at the table is similar with IPSC, right? Look at the table is very similar with IPSC, but the material located above the table, it's very complicated. Okay. Is there another feature I have? And I can show another picture. Oh, here. This is XRD equipment, a real XRD equipment. Here. This is XRD. This one, XRD ya. The real XRD equipment in the lab. Ya. Harganya yang 4 miliar ini mahal ya. Okay, so we continue to the slide. Yeah, maybe. Here. This sputtering, yeah, as I show you also the real equipment. And this is also the most expensive equipment to make a thin film, molecular beam epitaxy. Look at.
Yes, MBE. It actually stands for Molecular Beam Epitaxy System. It's a big vacuum chamber with several thermal evaporation sources. The sources are all aimed at a center point where you put a substrate. We can change the electrical properties, the optical properties, the thermal properties. I sometimes explain it as it's a way of spray painting with atoms. And by engineering these stacks of layers that we're building up with the spray painting process, we actually make what is the first stage of a working either electronic or optoelectronic device.
Every morning, Bob comes in, and the first thing he does is he calibrates his source cells by looking at the KSA 400.
I actually did try a competitor's instrument when I first set that machine up. To use a technical term, it sucked eggs. You know, I looked at the KSA 400 in particular at the time was a really powerful tool at a good price for analyzing electron diffraction patterns in an MBE.
And the 400 makes it extremely easy for him to get the data from the diffraction pattern, analyze it, and tell him what his growth rate is. You know, I'm guessing it takes him probably 5-10 minutes at most.
Bandit I use on a regular basis.
It's just kidding, yeah, Mufti. If I am a lecturer in the United States University, I will ask the government to buy this equipment. And I will study it a lot and hard, like what the professor do. Yeah, I know the knowledge, but we don't have enough money to buy this equipment, right? And also, I will show you this equipment directly. Just kidding.
The only tool that I know of that allows you to measure low temperature substrate growth is the Bandit system. It does things that no other temperature monitoring tool can do.
Maintaining the control of those low temperatures to within, say, plus or minus 10 degrees roughly is absolutely critical to getting reproducible material quality.
You can really fine-tune the quality of the end device that you want to grow.
What the MBE makes, or what I make with the MBE, I kind of compare to plankton. Doesn't sound very appealing or sexy, but you know what? Everything else in the ocean dies without good plankton to eat. The plankton not only has to be edible, it has to be really nutritious, or the orca, meaning the terahertz system at the top of the food chain, floats belly up in the ocean. Pretty graphic way of putting it, right?
To have that real-time control to then make a better end device is what Picometrics needs, and it's a very powerful way to control your end product.
What next? Here. Here. How does the mechanism of
PVD products PLD MBE and several of our other PLD systems are highly customizable and can be built with other types of deposition processes fully integrated inside the vacuum chamber, along with the pulsed laser deposition process. Our PLD MBE deposition options allow you to complete multiple types of depositions all within one chamber, making your work faster, easier, and reproducible. Deposition options include magnetron sputtering, effusion cells, atom or ion sources, RF substrate bias, and high-pressure read. Inside the vacuum chamber, standard programmable laser beam rastering provides more uniform target utilization and better film thickness uniformity on the substrate. This simulation shows the growth of a multi-layer film stack of 3 different materials using computer-controlled target indexing and laser firing. Any number of layers, up to 6 materials, can be grown. All PLD MBE systems come standard with 6 2-inch targets and can easily handle smaller targets. The multi-layer stack process can be repeated multiple times via software, and layers from other types of sources can be easily incorporated into the recipe process, as you will see. Along with the laser, other optional deposition sources can be used to create multiple layers. Our PLD MBE 2100 system can handle 1 optional deposition source. Our 2300 system can handle up to 3 optional sources. And the 2500 system can handle up to 5 optional sources. Such sources include 2-inch magnetron sputter sources that can be used either independently or in conjunction with laser deposition to add metallic, ceramic, or other types of materials. Effusion cells that can be used independently or in conjunction with laser deposition to evaporate specific materials in a highly controlled fashion. Atom or ion sources that can be used independently or in conjunction with laser deposition to provide atom or ion-assisted deposition for achieving chemical interaction with or for adding mobility to the growing film. The ion source can also be used for substrate pre-cleaning. Another option offered by PVD products is applying an RF bias to the substrate surface. This produces a plasma right in front of the wafer that can be used to pre-clean the substrate surface prior to deposition in a background of argon gas, or to conduct reactive film depositions of oxides or nitrides when sputtering or depositing films via PLD. This option does not occupy any of the ports on the back wall of the chamber, leaving them fully available for the other options noted, and thus can be integrated into almost any of our configurations. All PLD MBE systems can integrate with a high-pressure Stibe Instruments read system to be used to monitor the quality of thin film growth in situ up to pressures of about 200 millitorr. K-Space Associates hardware and software is also provided for full data acquisition.
Wow.
Multiple deposition, RF bias, and read options are just some of the many features incorporated into PVD's line of PLD MBE systems to provide thin film researchers with the most up-to-date technology, ease of use.
You know, because it was too expensive, there is no university in Indonesia having this equipment. Because it's the most expensive equipment for this equipment. But yeah, we just want to see if you are in the rich country, we can study it detail. Yes, so this multi-beam epitaxy, with the high purity of elemental sources. Groove interface, reads, grow, control, in situ surface analysis as described by the previous slide. And also another way to make here thin film is by pulse laser depositions. But I feel the time is near to Maghrib. So I believe that we can continue the material next week for the next discussions. Any questions? What your experience after attending today's meeting? So how excited are you?
Sir, I want to try make solar system in
summarize.
No,
Summarize.
I want to make solar system in our lab, sir.
Solar cell.
Yes.
Will we make a solar cell in lab? Inshallah. Make sure you have got vaccine, corona vaccine first, and afterward we will try to engage you and come you into our laboratory. The equipment is still in what? Not the equipment, the material. We have to import the material from the countries. Yeah, from the countries. Yeah, we are still waiting from the material. But while we are waiting for this material, we berapa ya harganya? 5 juta ya, gitu. That's for one material. We still have another material. I believe that the number of powder we have in the laboratory is more than the powder in IPSC lab. Jadi bahan-bahan powdernya di lab saya lebih banyak daripada bahan-bahannya di IPSC. Terus bahan-bahan yang saya itu jauh lebih mahal dan lebih banyak daripada selebnya lab IPSC, lab kimia. Aduh, but you will see your experience afterward. Inshallah. Yeah, I will want to make you come to our laboratory and we can perform some experiment. Yeah, you'll get a good experience, inshallah, in this course, modern physics. It will be special. And if you have any opportunities, you can also directly do a research, and afterward you can make like a paper and try to perform in international seminar or send it into international journal. Yeah, let's say next. Yeah, we will see, depend on the quality of your work afterward. Yeah, we have also 7 students for bachelor degree in physics department involving our research. Yeah, and also 2 master degree in ITB also involved in our research. And also special, the student in modern physics class entering in my lab. Wow. Okay, yeah. Okay, it's the first time IPSC student coming into my lab and do the activity like researcher. Okay, yeah. So maybe I feel it was enough, yeah, for today meeting. So what is your homework for today? Maybe you can summarize the content, yeah, what you have learned about diffraction phenomena, yeah, and atomic layer depositions. So that's the thing that we discussed in this meeting today. Thank you for your participation. And Atoila, Agnia, Dea, Rizky, is there? Oh, Amri, yeah, is Amri involved in this course?
No, sir.
Oh no, Amri, yeah, do not include in this course. Oh, okay. There's only 1, 2, 3, 4, 5, 6, 7 students. Is it right? 7 students entering the class?
Yes, sir.
Yes, sir.
Okay, I feel all students have come today. Thank you very much for your attendance. I'd like to say hamdalah, alhamdulillah, amin. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you, sir.
Thank you, sir.
See you next week. Yeah, inshallah.
See you next week, sir.
Yeah.